Hello, my name is Kelsey Horick, and I am enthusiastic to share some information with you that examines the effects of maternal vitamin B levels on the developing offspring. I have created a slideshow to assist in my demonstration. When I was first tasked with choosing a topic to research, I knew right away that I wanted to investigate a women's health or labor and delivery matter. So I asked myself, in my work as a labor and delivery nurse, what had I noticed in practice relevant enough to investigate? Over the last year, I had noticed a trend in screening for the MTHFR mutation among the women that we cared for. Now, some of you may not know what that is, and initially I didn't know much about it either, but researching the effects of maternal vitamin B levels on the developing offspring yielded many associations. Among them, support for practitioners to test for the MTHFR mutation. I hope you are as enlightened as I was as I discuss more details on the MTHFR gene and other correlations in maternal vitamin B levels and offspring outcomes. First, researchers have been curious if maternal vitamin B levels affect birth weight and gestational length of the developing fetus. Although a direct association was not found between initial birth weight and vitamin B levels, a correlation was revealed between vitamin B6 and the growth of the offspring. There was a positive association between optimal maternal vitamin B6 level during gestation and optimal weight gain shown when the offspring was 3 years old. Likewise, vitamin B12 deficiencies are associated with an increased risk of preterm delivery. Premature offspring are often smaller in size. Therefore, although there is no direct association between birth weight and vitamin B levels, there is an indirect association between vitamin B levels and the size of the offspring. This is evidenced by an increased risk in prematurity in vitamin B12 deficient mothers. Another reason why I was eager to research maternal vitamin B levels' impact on the offspring was because of all this stuff I have heard about folate over the years. It is common knowledge in the United States that folic acid is important during pregnancy. But what is all this folate and folic acid stuff really? Well, folate is simply the naturally occurring form of vitamin B9, and folic acid is the synthetic form. In 1998, the United States had gathered enough evidence that folic acid supplementation drastically reduced the rate of neurotube defects that food fortification laws were passed. Folic acid was then introduced into bread and cereal products. According to the United States Preventative Services Task Force, evidence still recommends that supplementation with folic acid daily provides more benefits than it does risk. The current recommendation is for all women of childbearing age to supplement with 0.4 milligrams to 0.8 milligrams of folic acid daily. At the bottom of the slide, you can see a figure depicting neurotube defects that can happen in folate deficient mothers. To my surprise, I discovered some interesting information regarding telomere and DNA biology and how that is related to varying B vitamins. Now, unless you work in the field of biology or epigenetics, you may be racking your brain, like I was, to remember the significance of telomeres. Allow me to refresh your understanding. The figure at the bottom of the slide represents a DNA strand, and the yellow tips at the end denote the telomere. According to the studies I examined, telomere strands are a part of the DNA that is non-coding repeating segments. The research suggests that these segments of DNA are related to aging, regeneration, and physiology. Because offspring with a shorter telomere length have a higher likelihood of developing many chronic health conditions later in life, a significant finding was that newborns born from mothers in the highest level folate group had a 10% longer telomere length than those newborns born from mothers in the lowest folate level group. This is a significant finding because cardiovascular disease, hypertension, atherosclerosis, heart failure, type 2 diabetes, and early mortality are related to shorter telomere length. Over Overall, the magnitude of maternal folate deficiency in regards to telomere length is equivalent to the effect of maternal smoking, hypertension, obesity, and diabetes on the developing fetus. Another important finding to mention regarding DNA and maternal B vitamin levels is the role that varying B vitamins play in the 1-carbon cycle or 1cc metabolic pathway. The 1cc metabolic pathway provides byproducts that are necessary for DNA synthesis. Without optimal vitamin B12, folate, and vitamin B6, the 1cc metabolic pathway is impacted, which interferes with DNA methylation. This interference can impact gene regulation at important stages in the offspring's development. In closing, I would like to mention the secondary effects of maternal homocysteine levels on offspring. These effects are important to mention because studies revealed a relationship between maternal B vitamin levels and maternal homocysteine levels. First, homocysteine levels are regulated by folate via the MTHFR gene. A species of folate, 5-MeTHF, is required for homocysteine metabolism. A mutation in the MTHFR gene, or suboptimal folate levels, have been shown to cause elevated homocysteine levels. Likewise, vitamin B12 and vitamin B6 deficiencies were shown to alter homocysteine. Homocysteine levels were elevated because vitamin B12 and vitamin B6 are not available in deficiencies for the 1cc metabolic pathway. The methyl groups yielded from the 1cc metabolism are necessary for homocysteine metabolism. It is important to discuss the effects of elevated homocysteine levels on the offspring because elevated homocysteine is associated with the development of preeclampsia. Preeclampsia increases the risk of medically induced preterm delivery and small for gestational age fetuses due to fetal growth restriction. Because a mutation in the MTHFR gene has been shown to cause elevated homocysteine levels and subsequently increase the risk for preeclampsia, this is evidence to support screening patients for the MTHFR mutation. In conclusion, research has shown that maternal vitamin B levels have an impact on the developing offspring. The maternal levels of particular B vitamins affect the length of gestation, the growth of the offspring, the likelihood of certain congenital malformations, DNA synthesis and integrity of the offspring, and the metabolism of homocysteine. The magnitude of these effects extends as far as the offspring's potentiality for developing certain conditions later in life. Lastly, I hope to have provided you with sufficient evidence for MTHFR screening if you start to see it in your practice. I've included information on where my research came from in case you are interested. If you have any questions about the effects of maternal vitamin B levels on offspring, please let me know. Thank you.